everyone, and welcome to the next Advanced Higher Chemistry video. Today we're going to have a look at chemical bonds and mainly the shapes of molecules. We're going to have a think about a new way of representing bonds, which is quite similar to the way that you've done since National 5, just to introduce the Lewis dot diagram so you're familiar with it. One new type of bond called the dative covalent bond, and then how we can predict the shapes of electron pairs around an atom and the actual shapes of molecules based on the number of outer electrons and things. So in terms of our chemical bonds, you've already seen polar covalent, pure covalent, ionic and metallic bonding. And I'm not going to go back through exactly what each of those are. That's straight through from National 5 to higher and a lot of revision. One diagram I'm just going to pop here just now from this is just quite important for you to be able to see. So this is just showing the energy associated with two atoms coming close together, or two nuclei coming close together. We're quite happy with the idea that a covalent bond is a shared pair of electrons, an ionic bond is a transfer of electrons, but the energy associated, like why these things actually end up bonding, is kind of shown here. So from here, this kind of goes backwards, it goes A to E here because we're talking about the distance between the two nuclei. So the axis here would be if they were touching the two nuclei together, which isn't going to happen. And then we've got our potential energy going up the y-axis. So at A, we're saying that the atoms are infinitely apart. So they have a certain amount of energy, that's the energy contained within those atoms at that point in time. And as they start to come towards each other, the potential energy in them actually decreases. Because remember, when we're talking about these bonds, we're talking about the nucleus attracting the electron from the other atom. And so that attraction actually lowers the energy associated with the atom that we're talking about. So we come through here, and as we get to C, we're getting much closer together. This is dropping down, and then we get into this kind of trough here, and this is our bond length apart. This is where essentially our atoms are held together in what would be a covalent bond in this case. So we're overlapping, if you look here, to be overlapping of that outer shell, or two nuclei, our electrons would be sitting in the middle. E is basically if we got those atoms too close together. You then have repulsion of the two positive nuclei from each other, and so all of a sudden this shoots way up in terms of energy. It's completely unfavourable and it isn't going to happen. So at point D here, we're quite happy these atoms are being held together. That is our bond length that's not really going to shift here, because any further away that energy starts to go up again, and any closer together it shoots up exponentially. So this is quite an important diagram just for you to be aware of when you're looking and thinking about the bonds in terms of our advanced higher chemistry knowledge. Now, moving on, we talk about a different way of representing our atoms, and it's only a small thing, but since National 5, say we were talking about hydrogen, we would have hydrogen, our nucleus here, we would have our shell, that would be containing an electron here, and then we'd have our second hydrogen atom, and we'd overlap the shell, and let's just represent that as a dot this time, just so that we know that that electron belongs to this hydrogen, that electron belongs to this one. The Lewis electron dot diagrams, much similar. All we're doing is getting rid of the circles that represent our outer shell of electrons. So I represented one like this and one like that. That would be my Lewis dot diagram, talking about a covalent bond, so my pair of electrons, my two hydrogens that are bonded together. Now I've obviously represented them as two different symbols. You'll very well just see them as being the same symbol. Either of those would be acceptable in this case. So this is what we're talking about, our Lewis diagram, or our Lewis dot diagram, if you ever see that. It is really important, just as it has been with these, to show all of the outer electrons. So let's take fluorine, for example. Fluorine has 7 outer electrons. So we'll say 1, 2, 3, 4, 5, and I'll go this way, 7. And then overlap, because remember we're talking about diatomic. It's a bond here. I'm just going to keep the symbols the same, just crosses for my electrons. That's what I usually do. So that's what we are used to doing since National 5. If I want to do my Lewis dot diagram, there's one fluorine, there's the 2 electrons in between them, but fluorine has its other 6 electrons as well. Okay, it's just a different way of representing them. We don't need to be drawing the circles. It used to get really messy if you think about nitrogen. Now nitrogen has a triple bond between the two atoms, and it's always looked a bit messy because you always want these to be at top, bottom, left and right, and it doesn't work with nitrogen, so you end up with 3 in here. It feels a bit cramped, and then its other pair of electrons here. All we would do in this case is we would have our nitrogen, and there's 1 bond, 2 bonds, 3 bonds, the other nitrogen, and then the other pair of electrons on the nitrogen atom. If that looks a bit confusing, if you're doing 2 different symbols, it might look like this. Okay, let's see, this is this one, and this is one here. Okay, these are our Lewis dot diagrams to be able to represent those electrons to show all of the outer electrons, not just the ones that bond in the middle, but the ones on the outside as well, if they exist, just like we did when we did our overlapping shell diagrams. So that's Lewis dot structures, Lewis dot diagrams. One really simple thing for you to be able to look at, one little bit of nomenclature for you to be able to think about. But the main thing that we're going to go on to is really start talking about these shapes of molecules. And another thing that I'm going to have to kind of define for you, if you like, in this point, before we have a look at the shapes, is this dative covalent bond. So we have a dative covalent bond. This is a nice new type of bond for advanced higher chemistry, and it's really quite simple. So if we're having a look here, in all of these, each one of these atoms is bringing an electron to that bond. Okay, this hydrogen brought 1 electron, this hydrogen brought another electron. Same with the fluorines here, they both brought 1 electron to form that covalent bond, and the same with the nitrogen. Each one of these nitrogens brought 3 electrons to make 3 covalent bonds. That's what we look at the sharing of electrons. But sometimes what we find is that we can have a species, a chemical, that can donate 2 electrons. It can donate basically both of the electrons to that. One example would be the creation of the ammonium ion. So we've used molymod kits in my classroom, and in the molymod kits, nitrogen sometimes has an extra space, and it's quite confusing because we know that nitrogen can form 3 bonds. Now, ammonia looks like this. This is my Lewis dot diagram. Ammonia, nitrogen has 1, 2, 3, 4, 5 electrons. Each of these hydrogens has 1 electron, and I've formed 3 covalent bonds. So that would be NH3. Okay, and what we're saying is that nitrogen has these other 2 electrons. If I have H+, for example, H+ is positively charged. This is a pair of electrons. This is a place where there is negative charge, essentially. Electrons have a negative charge. It's not a formal negative charge like a negative ion, but what can happen is these electrons can form a bond with this hydrogen, both electrons, the pair of electrons, and that would give me the ammonium ion. And I'm calling it the ammonium ion because, give me 2 seconds, I've done my dots and crosses the wrong way around this time, but that does not matter. As long as I remember that these 2 are from nitrogen, I then have another hydrogen in here, and this whole thing is positively charged. Okay, so this is NH4 plus as opposed to NH3, which is ammonia. Now, if you think about when we do our group ions, so in our data book, when we go to that table to try and work out the formula for different group ions when we're doing our formula writing, you've seen ammonium since National 5, we've just never really explained it properly to you. This is the ammonium ion. We've taken ammonia, it has formed a dative covalent bond, so both electrons coming from the same part of the chemical rather than one from each, and it's formed another ion. So this is my dative covalent bond for you to be aware of in this section of the course. So 2 little things really for you to have an idea about, but then we have to really have a think about our electrons and how we know different shapes of things. Like, how do I know that ammonia is going to be pyramidal like this? How do I know that this is going to be tetrahedral? This is something that we really need to have a little look at, and this is a section of our notes called Shapes of Molecules. For this section, there is a lot going on, so we're probably going to be looking more at the slides than we are at the page for the rest of this, but we might jump between the two, so we'll have a wee look. In terms of our shapes of molecules, we need to be able to predict the shape for any molecule using its valence electrons, so using its outer electrons. And we need to have an understanding about the fact that electrons are negatively charged, and because they're negatively charged, there is a repulsion in there, but that repulsion is different depending on whether things are bonding and non-bonding. So we'll have a look at this. Any molecule is trying to get the atoms and the bonds that are in it to create the least repulsion. So if you think back to that first page when I was showing you this diagram, which I'll just jump quickly back to, this was our lowest energy state for this particular compound. So what we're really looking at is for any compound, we want to reach the lowest possible potential energy within that, and the molecule does that by adopting a specific shape to keep all of the electron pairs as far away from each other as they can be. And that's all to do with the valence electrons, and we can predict the shape that these are going to take. So you have to have a think about bonding and non-bonding pairs. So with that ammonia, when we had NH3, nitrogen had a pair of electrons that wasn't involved in bonding. That's a non-bonding pair. It had 3 bonds. Those were 3 bonding pairs. We call this process valence shell electron pair repulsion, VSEPR theory, and you'll see it just written as VSEPR, which sometimes we'll just call VESPR, even though it's VSE and not VES. But you'll see it written as VSEPR more than it being written out. And this is the theory that you need to be able to adopt in advanced higher. So having a look here, we looked at ammonia already. So here's ammonia. Here's the Lewis structure, not the Lewis dot structure, but the Lewis structure, where we're seeing our 3 bonds and we're seeing our lone pair of electrons on nitrogen. Thinking about our electron pair geometry, we already knew about things being pyramidal here, but this pair of electrons that's on the top, I want to think about where the electrons are around nitrogen, and this is where we can get confused. You can either be asked what the geometry is of the electron pair, or you could be asked the geometry of the molecule, what shape the molecule is. So if you have a look here, this bond is a pair of electrons, it's a shared pair of electrons. So is this, so is this. This is a non-bonding pair of electrons. There are 4 pairs of electrons in this molecule, and the way that they arrange themselves is as far away from each other as possible, and that's in a tetrahedral shape. However, the actual molecule, you can't see these electrons. The actual physical bonds and atoms make this shape, and that's what I'm going to explain to you over the next few slides. So, the shape of these molecules can be predicted from the number of electron pairs that we have, both bonding and non-bonding. So if we take neutral molecules for now, so we take molecules that do not have a charge, so not ammonium, but ammonia, water, methane, anything like that. In order to work out the number of electron pairs, you need to take the number of outer electrons on the centre atom in the molecule, plus the number of bonded atoms, and you divide it by 2. So here's a wee example. If we have ammonia, again, we like to use this as our example. Now, ammonia, if you think on its number of electrons, it has an atomic number of 7. And so its atomic number 7 means its electron arrangement is 2, 7. So 2 in the first shell, 5 in the second shell. So the second shell, the outer shell, has 5 electrons. That's where this 5 has come from. There are 3 hydrogens attached to that nitrogen, so we add 3. So the number of outer electrons plus the number of bonded atoms, so 3 have bonded to the nitrogen, do not include the nitrogen, and then we divide that by 2 to see that there are 4 electron pairs. Now I know from this, nitrogen has formed 3 bonds, so there must be 3 bonding and 1 non-bonding, or you might see it referred to as a lone pair. Okay, so 3 bonding electron pairs, 1 to each hydrogen, and 1 non-bonding pair on that. And given that, that dictates that this is going to be trigonal pyramidal in shape, or pyramidal in shape. In terms of the shape of these molecules, there is some repulsion involved between bonding pairs and non-bonding pairs. So looking here, we have beryllium difluoride, or BF2, or BEF2, sorry. Beryllium has 4 electrons in total because it has atomic number of 4. So 2 in the first shell, 2 in the second energy shell. So only 2 electrons that can actually take part in bonding. So there's your 2 plus two other atoms bonding in. That's 4 divided by 2 means that there are 2 bonds. We know it's bonding to 2 things, so both of those pairs of electrons, must be bonding pairs of electrons. And it orientates itself to make sure that this pair of electrons in this bond and this pair of electrons in this bond are as far away from each other as possible, and so there's 180 degrees between them, and so it is linear in shape. This is how we determine these exact shapes. Okay? Let's have a look at boron trichloride. Boron has 5 outer electrons. 5 electrons in total. So it has 2 in the first shell, it has 3 in the second shell. And if it has 3 in the second shell, it's 1, 2, 3 bonds it can make with those 3 electrons. Okay? And if it's forming those 3, you've got 3 in its outer shell, plus 3 here. Divide that by 2 gives you 3 bonding pairs of electrons. There are no lone pairs in here. They arrange themselves so that they are as far away from each other as possible. And the way that they've done that, so this pair of electrons, this pair of electrons, and this pair of electrons, to be as far away from each other as possible, then it is trigonal planar, and the bond angle is 120 degrees. So a trigonal planar shape is completely flat. So if we just quickly look at the page again, if I have boron here, I have chlorine here, and chlorine here again, there's 120 degrees between the bonds here, and it's completely flat. So it would be in the plane of this page. There is nothing sticking up, there is nothing sticking down. This is the furthest away that these 3 bonding pairs of electrons can be from each other. Okay, so it's completely flat. Trigonal planar, that's where the planar part comes from, it's on a plane. Okay. If you have a quick look at the next one then, 4 bonding pairs. So we're looking here at methane, carbon with 4 hydrogens. Carbon has 4 outer electrons, so 4 electrons in that second shell. It has 4 atoms bonded to it, and so that's 8 in total. Divide that by 2 gives you 4 electron pairs. Because we know that there are 4 hydrogens bonded in, each one of those electron pairs must be a bonding pair. The shape that we've known since National 5 is tetrahedral. The bond angle for these ones is quite important, you need to know them. It is 109.5 between each of these bonding pairs of electrons. So in a tetrahedral arrangement, those bonding pairs of electrons are as far away from each other as possible with a bond angle of 109.5. Note that the word planar isn't in there because it is not on the plane this time. You have bits that are sticking up and down from the page. Moving on to 5 bonding pairs now. PCl5 is an interesting one. So we have phosphorus and we have 5 chlorines. Now, phosphorus has an atomic number of 15. So if you think atomic number of 15 means we go 2 and then 8 and then 5 would be the way we used to do our things. We're not thinking about our S and P orbitals just now. There are 5 electrons in its outer shell plus 5 chlorines adding in makes 10. Divide that by 2 gives me 5 pairs of electrons. I know there's 5 things bonding in, so each pair must be bonding, and so we have 5 bonding pairs of electrons. The shape of this is trigonal bipyramidal, and what I want you to think of here is if you're looking, there are 2 different bond angles. There is a 90 degree bond angle and there is 120. So think of the way that I wrote that boron trichloride. Think of this phosphorus, these 3 chlorines being on the plane of the page. So let me draw that out really quickly. If I have phosphorus with 3 chlorines on the plane of the page, okay, this is my 120 degrees, which you already saw in boron trichloride. The only difference now is the other 2. I have one that's sticking directly up from the page. I have one that's sticking directly down from the page, because ignore that scoring. went like that with my pen. So there's one sticking up from the page and there's one sticking down from the page. So it's almost like, here's a triangle, yeah? And I have one sticking up here, so it's like a wee pyramid. And it's bipyramidal because underneath there's another one that's like two pyramids, one on top of the other. Okay, one sticking up, one sticking down. That's why it's trigonal bipyramidal. It's 90 and 120 degrees in here. And then our last one would be for 6 bonding pairs, just looking back at that slide. SF6 now, so if I'm looking at sulfur now has 16, so we're just adding one more into that outer electron from outer electron shell from phosphorus. We have 6 electrons in the outer shell. I have 6 fluorines going in, so that's 12. Divide that by 2 gives me 6 pairs of electrons. 6 pairs of electrons, 6 things bonding in, they must all be bonding pairs. The bond angles in this case are all 90 degrees. So here, this sulfur, 4 of the fluorines are in the plane of the paper, one sticking up and one sticking down. So this is like a square-based pyramid sticking up and another square-based pyramid sticking down if you think on the shape of it. And all bond angles are 90 degrees. Now the really confusing bit here, this is an octahedral arrangement. There is nothing to do with 8 here in terms of the electron shells. It actually, if you think of this as a solid shape, it would have 8 faces, which is where the octahedral comes from in its name. So we can summarise the electron pair shapes by this table here, and really if we're looking at 2 electron pairs, then the arrangement of those pairs will be linear, 3 will be trigonoplanar, 4 will be tetrahedral, 5 will be trigonal bipyramidal, and then 6 will be that octahedral shape. Now, this is only for those electron pairs. This is whether they are bonding, non-bonding, a mixture of the two. That is the arrangement that you can expect to have if that's what you have around that centre atom in a molecule. Now, we need to have a think about when in a molecule we have both bonding and non-bonding pairs, because what we've seen so far has really just been looking at a lot of bonding pairs and not really thinking about repulsion between those electrons, because these electrons are negatively charged, and this is quite important when it comes to these shapes. So looking at these 3 examples just now that I have on the slide, when a molecule has a lone pair, the bond angle will decrease. The lone pair will actually repel these bonding pairs of electrons in the likes of ammonia here. This lone pair has greater repulsion to this bonding pair than another bonding pair does. And so it pushes it. That's why we've always got you to draw these in certain ways when we talk about the shapes of molecules in National 5 and higher. So having a look at our methane just now, looking at 4 bonding pairs, the shape of those electron pairs in that molecule is tetrahedral, as is the actual molecule shape itself. So I will have a look at some molecular models of this in just a wee second once I talk through everything else that's on the slide. The ammonia also has 3 bonding pairs in this case, but there is a non-bonding pair of electrons as well. So it also has 4 pairs of electrons. Therefore, the actual electron pairs shape is tetrahedral if you look at the way that they're all from each other, except these have been pushed slightly closer together. But the actual shape of the molecule is pyramidal or trigonal pyramidal, you'll see. And we'll look at that in a second. And then to an even greater degree here, having a look at water. Water has 2 bonding pairs and 2 non-bonding pairs, 2 lone pairs on the oxygen. Now that is showing me that, again, I have a tetrahedral arrangement of the actual electron pairs, but the molecule itself is angular. And we know here our bond angle was 109.5. Changing one of these bonding pairs to a non-bonding pair has decreased the bond angle to 107. Adding in another non-bonding pair and removing a bonding pair again has given me 2 non-bonding pairs and 2 bonding pairs, with that bond angle being 104.5 degrees. So it's pushing them ever so slightly closer together because there is a greater repulsion to the lone pairs. So just to show you that in terms of molecular models in 3D, so have a look at this. Here is methane. So we have carbon in the middle. Now carbon had its 4 outer electrons. There are 4 hydrogens bonded in, so that was 4 plus 4 is 8, divided by 2 makes 4 pairs of electrons. all 4 pairs are being used in bonding, so it has 4 bonding pairs of electrons. The shape that you get for the electron pairs is tetrahedral, but the whole molecule is tetrahedral as well. Now we have ammonia. Ammonia, nitrogen has 5 outer electrons. There are 3 hydrogens bonding in, so 5 and 3 is 8, divided by 2 is 4 pairs of electrons. Now in this case, only 1, 2, 3 are bonding pairs. So on the top here, where we still have another wee kind of hole for another bond, this is where my lone pair of electrons is. The pairs of electrons are tetrahedrally arranged because there's one at the top and these 3 coming out. So imagine another one, I could even stick another bond in here. It's not going to anything, but this could be my lone pair of electrons. Still tetrahedrally placed around about the central atom. However, ammonia itself, the shape of the physical molecule with the physical atoms, is trigonal pyramidal or pyramidal now. It's not tetrahedral. So the electron pair shape is tetrahedral, the molecule shape is pyramidal. Then we can have a look at water. Again, imagining there are 2 lone pairs on here because oxygen had 6 outer electrons with 2 hydrogens bonding in, that's 8, divided by 2 is 4. This time only 2 are being used to be bonding pairs of electrons. The other 2 are invisible to us here, are non-bonding pairs. Those 2 non-bonding pairs are pushing these even closer together, and we get this angular shape of the molecule, but the shape of the electron pairs around the oxygen is tetrahedral. There are 2 separate things to think of there, so just be careful with that. In terms of the repulsive effect, having a look back at the slide, you have an increase in repulsion as you go to non-bonded pairs. So the least repulsion exists between 2 bonded pairs of electrons. Then as you go to a 1 non-bonded to a bonded pair, you have slightly more repulsion, and then 2 non-bonded pairs of electrons would have a greater repulsion and would try and be as that would prioritise being further apart around that central atom. So if you have bonded pairs, they can go closer together to allow the non-bonding pairs to be further away from each other and away from the bonding pairs of electrons. So this gets complicated quite fast, just seeing all the different shapes. So in terms of this is quite a useful few things. I've got another wee table that I'll show you in a second, but I'll go through it on the slides just now. We're having a look here at the total number of electron pairs. If we have 2, they can only be 2 bonding pairs and it's going to be linear. I don't really like using carbon dioxide as an example here, but it's the only one that I could find. But 2 bonding pairs, we're going to be talking about something that's linear. Looking at 3 electron pairs now, there are a couple of options. You might have the base, just for the electron pairs, is trigonal planar for these 3 electron pairs. Doesn't matter if they're bonding, non-bonding, the electron pair geometry is trigonal planar. So if all 3 are bonding pairs, then the molecule will also be trigonal planar. If 2 of these are bonding, but one of them is a non-bonding pair of electrons, then it will be bent or angular or V-shaped, however you tend to say that. Okay. Going to 4 pairs, there's a few options. The electron pair geometry, so 4 pairs of electrons, regardless of whether they are bonding or non-bonding, form a tetrahedral arrangement around about that central atom. I've lost my mouse, there we go. So this is a tetrahedral arrangement of the electron pairs, does not matter if they are bonding or non-bonding. So if all 4 are bonding, then the molecule is tetrahedral. If 1 is non-bonding, so 3 bonding and 1 non-bonding, that's where we get our ammonia, or trigonal pyramidal shape. And if you have 2 and 2, 2 bonding pairs, 2 non-bonding pairs, then you will get an angular bent V-shaped molecule again, okay, with the lone pairs still adopting that tetrahedral arrangement around the central atom. So the moral of the story, kind of going through this, is whatever the electron pair geometry are, if it's all bonding pairs, then that is the molecular geometry. If you have a non-bonding pair, then it's not the same as the electron pair geometry. Now looking at 5 pairs, you have, this is a trigonal bipyramidal. So what we mean by this for the electron pairs is you have a triangle but here's like the top of a pyramid almost, and here's almost like an upside down pyramid. So trigonal, 3, bipyramidal, 2 pyramids. If all 5 are bonding, then the molecule is also trigonal bipyramidal. If 4 of these are bonding and 1 is non-bonding, you get something called a seesaw shape. If 3 are bonding and 2 are non-bonding, then you get T-shaped. And if you have 2 bonding, but you have 3 non-bonding, then you end up with a linear shape. And here are a few examples just going through this. Okay. And then finally, if we have 6 pairs of electrons, they arrange in an octahedral shape. This is the one that gets confusing again, is that it's octa meaning 8 because there would be 8 faces. If you think of this being a square in the middle and you go up to a square-based pyramid, there'd be one face here, another face here, one at the back and one at the side, so 4 on the top and then another 4 on the bottom. That's where the octa part comes from. But 6 electron pairs, if they're all bonding, the molecule will also be octahedral. If 5 are bonding, 1 is non-bonding, you end up with square pyramidal. So here's a square, 1 on the top, non-bonding pair sticking at the bottom there. 4 bonding pairs and 2 non-bonding, you end up with square planar. And here are a few examples in here. So that's quite a lot on a couple of different slides. I do have this in quite a nice little table, I think, actually, if you can see that okay there. This is just showing, we're saying here about number of electron dense areas, so where number of those electron pairs essentially, so 2, 3, 4, 5 and 6. Here is your electron pair geometry: linear, trigonal planar, tetrahedral, trigonal bipyramidal and octahedral. If you have no lone pairs, if they're all bonding, then these are the same. If you have one lone pair, it changes to, and you can see how that changes as you go through. So this is quite a nice little table, just kind of summarising everything that's on there. It is a lot to take in, just really thinking about these electron pairs and what this actually means for the shape and the geometry in here. So quite a bit to take in, memorise and be able to work out. Quickly just moving back to the slide just before I finish. You might have a polyatomic ion. I'm just going to put all of this up here just now. The general rule here is if you have a negative charge, you're going to add an electron to your sum. If you have a positive charge, you're going to take one away. So here, electron pairs, again, 5 is because nitrogen's my central atom. It has 5 in its outer shell. There are 4 hydrogens attached, but because it is positive, I'm taking away 1 because one of those hydrogens is bonding through that dative covalent bond here. And so it's not actually brought an electron to the bonding. So again, 4 electron pairs all bonding. This is a tetrahedral shape, but the whole thing has a positive charge. If we have a negative charge here, so boron tetrafluoride, boron had 3 electrons in its outer shell. There are 4 fluorines. Add 1 for a negative charge, that makes 8 divided by 2. 4 electron pairs, all are bonding. This is tetrahedral again, negative charge. Okay, so you add an electron if you have a negative charge, you subtract 1, if you have a positive charge. Just something to remember. And finally here, just one really quick one to note that can come up is that chlorine trifluoride will adopt this stable T-shaped structure. 3 bonding pairs and 2 lone pairs might not be quite what you expect, but it adopts this T-shape because it's incredibly stable. So just chlorine trifluoride, ClF3, not something you would maybe think about, but it's just one to point out in there. This can be quite complicated, quite a lot to take in, so it's really a case of looking over this, practising, finding examples that you can try to be able to work out what the number of electron pairs would be and what that would mean if you had one bonding and the rest non-bonding kind of idea in your head. So that's where I would start with this if I was going to be really trying to commit this into my brain, as I'd be sitting there thinking, right, okay, if I have this number of electron pairs and they are all bonding, this is the shape it would be. But if one of those was now a non-bonding lone pair, then what does that mean? That means that the other ones all get pushed slightly together and that changes it to this shape. And that's the reasoning that I would give myself as I were going through this. So that is kind of everything on shapes of molecules at the moment. I'm not going to go through any kind of other examples. I think I've spoken to you for quite long enough for this one. So good luck with getting all this into your head, and I will see you in the next video.